Welcome to Math 31. This is a lesson that examines, well, what I've called limits at infinity. What this really is, limits as x increases or decreases without bound. So in other words, x gets bigger and bigger and bigger, and y gets whatever. In fact, that's what we want to determine, is what is the behavior of y as x increases or decreases without bound. So to shed a little light on this topic, let's consider the following basic functions. The limit of 2x as x, as it's written, approaches infinity, but this means x gets bigger and bigger and bigger and bigger. So for example, x is 1, x is 2, 3, x is 100. And what you're trying to figure out is what is the behavior of y in y equal 2x as x increases. Now there are people who solve these problems by just subbing in x values, and it really works. Like you could say table of values, here's your x, here's your y. X is 1, x is 100, x is 10, x is 100, x is 1,000. And analyzing, what is y doing? Y is 2, y is 20, y is 200, y is 2,000. So what's happening is the y value is also increasing without bound. So I will indicate it like that, plus infinity. And it is still correct to say no limit. But this is actually better because it gives more information. You're saying, well, it's increasing, increasing, increasing. So you're giving more information about the behavior of the function as x increases. So I would prefer that, and you're going to find when you start graphing these, you care about that. You want to know whether the graph is increasing or decreasing. Now pay attention to that first example because we see variations of that throughout. And then the next one is also very common, even more common. The limit of 1 over x as x increases without bound. Well, play dumb with this one, and you set up a table of values, x and y, and x is 1, x is 10, x is 100, etc., like that. And the y value is just the reciprocal. So it's 1, 1 over 10, 1 over 100, etc. So what we see happening is the y value is getting smaller and smaller, but not negative. So it's approaching 0. The numerator is staying the same, and the denominator is increasing. So that ratio will always mean your number is going to get closer to 0. Wouldn't even matter if the numerator was 2 or 3 or any number, as long as it's staying the same and the denominator is increasing. Now, in general, we can make these observations. The limit of nx, where n is greater than 0, but n is otherwise a real number, is always going to be infinity. That is, it's going to be increasing without bound. This would be true if it was x squared or x to the 4, things like that. So there's a few things we need to be aware of with it. But this gives you an idea of what the nature of these problems. And then the other one is, like we saw earlier, variation of, that the limit of 1 over x to the n is equal to 0. And this would be true, again, assuming that n is greater than 0. If you have a negative exponent on the bottom, then when it comes to the top, that changes things. These are the two main guiding principles. Now let's do some examples that will require things like this. Now the language is always a problem because the tendency is to say as x approaches infinity. Technically, reminder again that what you're saying is x increases without bound or x decreases without bound. And there is a subtle difference. And in fact, you might get your knuckles rapped at some point. For me, it's not such a big deal because the work is done on paper. And so when you're working it out on paper, it's all the same thing. You do want to be clear on what's going on with it, though. Infinity is not a number. So saying x approaches infinity is a little misleading. You really mean x is getting bigger all the time. Anyways, here we have the limit of 1 over x to the 7 as x approaches negative infinity. Now this means x decreases without bound. And nature of this problem is we end up getting, you can set up a table of values if you want. Always works if you don't see what's going on. But if x is like negative 1, then negative 10, negative 100, you'll see that you're going to get 1 over negative 1. 1 over negative 10 to the 7. And it really works the same way as when you had getting bigger without bound. It's still going to be 0. It's just approaching from the opposite direction. Your numbers are going to be negative, but they will be approaching an asymptote of y is equal to 0. And then with this one, x approaches negative infinity. Again, x is decreasing, getting smaller and smaller and smaller. The thing of it is, we take those numbers, square them, they become positive and very large. Multiply by 3, and they're even more positive and large. So the limit here is positive infinity, or no limit. So the exponent matters quite a bit. Next problem brings up a new issue. We have a cubic polynomial. X is getting bigger and bigger and bigger. The key, pay attention to the leading term. I don't care about the 5x or the 2. Really just care about this first x cubed, because that's the one that's really dictating what's happening with the function. In fact, even graphically, it's the cubic, the leading term, that will tell you what that graph is doing. And in this case, x is getting bigger and bigger and bigger, but then we multiply by negative 4, and we end up getting a negative value instead. So as x gets bigger, y gets smaller without bound. And you can always plug in numbers if you're not sure. The next batch of questions, number 4, doesn't break a lot of ground, but as x gets bigger and bigger and bigger, looking at the leading term, we raise it to the power of 4 multiplied by 6. Well, the y value is also going to be increasing. At whatever rate, we don't care. At the rate that it's increasing, this is just about where it's ultimately going, and where it's going is upwards. So the 2x and the 1, just passengers. Just that 6x4 we worry about. Now number 5 is an interesting problem because some of you might be tempted to FOIL these out. Could do that. But in fact, you can sort of muscle your way through, thinking as x gets bigger and bigger, this factor is also increasing. And so is this factor. So it means the product of those two increasing numbers is also going to be increasing. Number 6, the limit of 4 to the x as x gets smaller and smaller and smaller. This one's misleading. It's not a polynomial function. It's an exponential one. And if you were setting up a little table of values to make sense of this, pick values for x, say negative 1, negative 10, negative 100, and you see what happens. 4 to the negative 1 is equal to 1 over 4. And then 4 to the negative 10 is equal to 1 over 4 to the 10. So what's happening is with that negative exponent, we are getting a stable numerator and a larger and larger denominator. So it's going to be approaching 0. Same scenario we saw before. Excuse me. Now, what we've been doing up to now is just kind of reasoning our way through it, and you get an idea of what's going on with it, and that's very important. But with rational expressions, we follow a method more. And starting off today with just this question number 1, with this, a rational expression, of course, is a fractional type problem with a numerator and a denominator. And we develop a method, or we use a method that we can use to put these in a form where we can interpret it. Because it's hard to know what's going on now. And some of you would be comfortable, okay, I'll plug in x is 1. What do I get? Then I'll plug in x is 100. What do I get? Then x is 1,000. And you can Armstrong your way through. But what I would recommend is follow this method. So what we do is we factor out a power of x from each term. And the factor you should take out should be, by my recommendation, be to divide by the highest degreed term in denominator. So some of you will choose to divide by the highest degree term on the numerator, and it works. It doesn't really matter. I like this because it's a little easier to interpret, but we'll have an opportunity to play around with that format later on. So what I do is each of those terms, I factor out an x squared, because that's the highest degree term of the denominator. So for the first question, at least, I'll divide the numerator by x squared, meaning that's 3, and then this is 6 over x squared. Because that's all you can do. You wouldn't normally factor that way, but 6 divided by x squared would be written like that. And then the denominator, x squared, factors out, and we get 4 plus 2 over x squared. So when we divide out those factors of x squared, top and bottom, we get this. And now we take the limit, and we fall back on those principles that were established earlier. 3 is unaffected by x increasing, but 6 over x squared would be 6 over 0, or it would be equal to 0, 6 over an increasing denominator. And then this is 4 plus 0. So this is equal to 3 over 4. That's the method. Let's take a look at another one. Only thing that's different with this one is the fact that the denominator is not in descending order. But we can do it a little bit more quickly. So what I would advise you to do for this problem is, instead of actually factoring and then dividing, divide each term by x squared. So that 3x squared divided by x squared, because x squared is the highest power of x in the denominator. So 3x squared divided by x squared is 3. X divided by x squared is 1 over x. So that would be x over x squared, which would simplify down to 1 over x. And then minus 2 over x squared. Then 6x divided by x squared is 6 over x. X squared divided by x squared is 1. And then 3 over x squared would be your denominator for that. And then when you take the limit, you'll see you'll have 3 minus 0 over 0 minus 1 plus 0. And that is just equal to 3 over negative 1. So that's negative 3. These type of questions on exams will be like 1 mark, maybe 2 max, because if you haven't already, you'll discover some patterns that can get you the answer like immediately just by inspection. Let's still do a few more. Number 3 is this, and this is an example of where we get one that is not the same power of x on the top and the bottom. So I don't view that as a big problem. I'm going to stick to my method, which is I will divide out by the highest power of x in the bottom, that x cubed. So 3x squared divided by x cubed would be 3 over x. And then 6x divided by x cubed is 6 over x squared. And then 1 divided by x cubed is just 1 divided by x cubed. And then on the denominator, we get 5. 2x squared divided by x cubed is 2 over x. And then this is 3 over x cubed. And then as we take the limit, we'll see we'll get 0 minus 0 plus 0 all over top of 5 plus 0 plus 0. So that's 0 over 5, which is just equal to 0. So the method works. It puts it in a form that we can make sense of it, and that's really what this is all about. Take a look at number 4. Now, number 4, here we have the higher power on top. So by the way, as always, stop me and go through this question yourself, and that's fine. So for this one, I'll look at it two ways. First off, I'll do it the conventional way that I've been doing. I will divide by the highest power on the denominator, which is x cubed. And that means we get 4x squared on top, and then minus 1 over x cubed. The denominator, 3x cubed divided by x cubed, is 3 plus 7 over x cubed. A little messy over here, but when we take the limit, we'll get 4x squared. Well, as x gets bigger, that's just going to be an increasing number on top. So it's going to be increasing. And then the denominator is 3 plus 0. Now when that happens, when you have an increasing number over 3, the denominator doesn't really matter. It's still increasing. So the correct answer is that this is positive infinity. 4x squared is going to get bigger and bigger and bigger. The denominator stays the same. Now the other method that you could have done with it is divide by x5. And if you had done that, here's what you get. We get 4 on top minus 1 over x to the 5. Then the denominator is 3 over x squared plus 7 over x to the 5. And when we take the limit, we end up getting 4 minus 0 over 0. And this means there's no limit. If you get a number on top and a non-zero number on top and then 0 on the bottom, it means no limit. Problem is, of course, it's harder to interpret. And second off, that you don't know for sure if it's going in the positive direction or the negative, although you'd probably conclude it's in the positive direction. And it's nice to know that, whether your graph is increasing or decreasing. So I favor dividing by the highest in the denominator. Now, number 5, I won't bother doing because it is really the same sort of thing. Here, I would also divide by x squared. Some of you are also going to notice patterns. What happens, for example, if the numerator has a higher exponent than the denominator? Well, in fact, the same thing always happens. So you can tell. Now, the only thing that's different with this one is the fact that x is getting smaller and smaller. So, in fact, I'm going to go through this one anyways, even though I just said I wouldn't. But pause me and feel free to have at her. We divide by x squared. We get x minus 7 over x plus 4 over x squared, and then this is x squared divided by x squared is 1 minus 3 over x squared. So when we take the limit, we get zeros, and we get x over 1. And when we take the limit now, x is decreasing without bound, so therefore the function will be decreasing without bound. The only thing that's different is that we're going in the negative direction. So you want to watch that carefully to make sure that your variables are all in, or your exponents are all doing what they should be doing, because the choice would be positive infinity or negative. But when we get it down to that simplified form, we should be able to tell. Number 6, nothing crazy happening here. You can always break down limits into two separate limits if you want, and that's a method that will work. Some of you won't bother with this, but I'm gonna do this. You can see what's going on. So as n gets larger and larger, the property of limits is such that we can split this one up, plus the limit as n approaches infinity of 4n plus 1 over n minus 2. And then when we divide by n squared on that first limit, we will get 3 plus 2 over n plus 1 over n squared over top of 2 plus 1 over n squared. So that's 3 over 2 when we take the limit. I'll go there fairly directly. And then the second expression, divide by n, is 4 plus 1 over n, and then 1 minus 2 over n. And that will give us 4. So 4 plus 3 over 2 is 5 1/2. You could have got a common denominator and cleaned them up like that, but this is more direct. So don't forget about those limit principles. Once in a while, they come in handy. Now I think I just got one more here to do, just a radical question. So this is a fairly easy question, but it's something we need to be aware of. So I'll bring up the next screen because it can mess you up a little bit. We have the square root of x squared minus 16 over x. And I'm going to note right away that the numerator is positive, denominator will be getting negative as this gets smaller and smaller. So therefore, we would say that this problem, this must be negative. So I'll write negative like this, shorthand. Positive numerator over a negative denominator will always give you a negative answer. Now, one way to do this one, there's really two. What some people will do, they'll look at this and they'll say, well, this is the square root of x squared minus 16, all right, but they'll also take that denominator of x and realize that could be written as the square root of x squared, which is just equal to x. So you express the non-radical term as a radical. And then they write it as a single radical, which is x squared minus 16 over x squared. And then you actually have choices. You can do it strictly by the book. And remembering a limit property, you could be taking the square root of all of these. Most people don't have instant recall of limit properties, but this would be correct. And then when you take the limit, you divide everything by x squared, and you'll take the limit, and you'll get the root of 1 minus 16 over x squared over 1. And then this is the root of, well, that's 1 over 1, so that's equal to 1. And don't forget, it's going to be negative 1, because the expression has to be equal to negative. So this is going to approach negative 1. Oops. Now the other thing you can do is just examine really what's the numerator looking like. It might occur to you that the 16 is of very little consequence. The term that's affecting things is the x squared. So you take this, the root of x squared minus 16 over x is really the same thing as, well, the root of x squared is just x over x. So we note the root of x squared minus 16 is just equal to x as x approaches infinity, or negative infinity. So this is just equal to 1, and then again we are aware that that's negative 1 because we're getting smaller and smaller. So that also works. It's just dealing with the principle that the leading term is the one that we're concerned with. The most popular method is method 1, where you express the entire thing as a radical. So I'll even make that note, express denominator as a radical. What we've done today then is limits as x increases or decreases without bound. Guaranteed that you'll get test questions like that, and you basically want to be shooting at 100% accuracy with these ones. If you have to Armstrong them, you can. Thank you for your time.